Hello everyone, February the 10th. Alright, let's go right into it. Shortest path with alternative color. I've done this before. Alright, you're given an integer n, number of nodes in a directed graph where the nodes are labeled from 0 to n minus 1. Each edge is red or blue in this graph, and there could be self-edges and parallel edges. You are given two arrays, red edges and blue edges, where red edges indicate there is a directed red edge from A to B. Blue edges, okay, the same thing. Return an array answer of length n, where each answer x is the length of the shortest path from node 0 to node x such that the edge colors alternate along the path, or -1 if such path does not exist. So we in the BFS kind of deal. So the first one we have 0 node and 1 node. So we have 0 to 1, which is a red, and 1 to 2, which is a red, and blue have no edges. So answer 0, 0 is just by itself. There's no the shortest path, so 0, 0 is always 0. So 0, 1 is fine. It's always, as long as there's a path, it's going to be 1. And 0, 2 we don't have because 0, 1, 1 to 2, they're all red. Okay, so on second example, red edge is 0 to 1. Blue edge is from 2 to 1. So 0, 0, 0, 1, 0, 2, 0 cannot be reached to. And we want to find the shortest path from node 0 to node x such that the edge colors alternate along the path. Interesting. Okay, let's see. And then 0, 0 is always 0. 0, 1, as long as there is edge, it's going to be 1. So the question is 0 to 2, right? Oh, if 0 to 2, that can be as well. So we start from 0 and we go traverse 1, right? 1 round, and then we get everybody that I can reach, 0 to 1, which is fine. Oh, they can be self, which means if I can go to myself, does that count? That's a good question. You say can self, right? It can self. And it has to be alternating. So one edge has to be red, one edge has to be blue. Yeah, so I'm thinking like, say 0 to 1. What if, right? What if we have this? 0 to 1, 1 to 2, 1 to 1. Right, so a 0 to 1 is a red. 1 to 1 is a blue. 1 to 2 is, so that would be interesting. So I think it should be 0, 1, 3. Yes, 0, 1, 3. Okay. So basically, it's going to be BFS, but we can redo the same edge if the next edge is of a different color, right? Basically, we just don't really care. which is BFS, okay? We BFS and we just keep going, and as long as the next edge is the same color, then we can stuck in a loop, right? We're stuck in a loop. Like I say, 0 to 1 is blue, red, 1 to 0 is a blue. Then we just 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0. Right? We constantly in a loop. So how do we prevent constantly in a loop? If you are 0 to 1, right? You can go to yourself, but you cannot go back. Because you go to yourself, you can. When we can argue, you go to yourself because you can readjust the sequences. But if you go back, you go to a node that has been visited before, then you're just doing circles. All right, that's because as you go, every edge is going to be alternating, and then you just go back just to make it alternating again. Why? All right, why? So we can allow self, right? We can allow from one node going to itself, but we cannot allow that it go back to some node that has been visited before. Right? We can go from myself, I can go to myself, which is okay, because that we can shift, right? It has a value. But if we go backwards, right, there's no point in going backwards. You already visited that node. So that's how we're going to prevent infinite loop. And when you go to yourself, you can go to yourself infinite times, right? You go to yourself. I mean, there will be an edge go to you, right? A certain color. And if they go to yourself, a different color, so you take that. And from yourself, and you go it again. But the previous is a different color, so you cannot take it again. No, you won't. No, you won't. And then you just, keep going, BFS this, and then try to see if you will hit every single one. Yeah, when you hit, then you do it. We can try. I think this is an interesting question. So, start with 0. Right, rest 0 is always going to be 0. I don't have red edges. Oh, we need... Ooh. Alright, we need a graph. Oh, do we need 2 graphs? Red graph, red G. Okay, and the blue. Okay, RG, BG, blue graph. Okay, then we are going to say for AB in red edges, R graph A dot append B. For AB in blue edges, B graph A dot append B. Okay, now we have the 2 graphs. We have this, we have result. And then while Q temp equals this for visited. Okay, visited equals a set. For node in Q. Okay, so for each node in Q, then we say visited or add Q, add a node, right? Actually, I'm not a fan of doing it here. I'm a fan of adding it. Because if we do horizontal, that's no use. So I'm more of a fan for each node, right? And then we need to know the previous edge, what color it is. right? The color. So we need to know the color. So it has to be 0 and then color. What color it is? Well, in the beginning we don't have a color, right? Beginning we do not have a color. Okay, so we don't put a color at the beginning. And maybe what we can do, what are you thinking? Times -1, right? So if we start with a 0, now a star we want to know, we want to do like it can be both. All right. We can do it 2 times. We can do it 2 times. Right? We can do it 2 times. Yeah, let's do it 2 times. We have the rest, right? And then we can call. Yeah, let's do this. We can do like a, you know, we can do a def BFS, right? And then BFS we can say initial the first path. Right? We can do a 1 or -1. If it's a 1, the next one we go no, exclusive or, which means what we can do is we can say graph, right? And that's the first graph, right? And then we also have a second graph. So 2 graphs, put it together, right? And then this just will be graph 0. And this will be graph 1. And then first color int, and we'll return nothing. All right, and now we can say in first color equals 0. That's red. First color equals 1. That's going to be blue. Okay. Now what we're going to do is we'll do this. We have a Q, right, equal to start 0 and first color. Okay. And then this equal this. Well, this and this for node pre-color, right? In this, what we're going to do, we're going to get the next color, right? Get the next color. So for so next color equals pre-color exclusive or 1. So if pre-color is 0, the next color is going to be 1. Pre-color is 1, next color will be 0, right? Then we say for next in graph next color node, right? We say if node is not invisited or node is equal, not node is next, right? If next is not invisited, then we can definitely visit it. Or if it's invisited but next is equal to node, then we give it another chance, right? Because it's a different color, so we'll do it again. But there's no point going back, right? We're going here to ourselves, because if you go back, then you just go down again. Ooh, hold a second. You can go back. Oh, you have to do the edge that leading you. If you go back, it's a different color. Then you can, right? So we say if next color is not visited. If it is, we cannot do. But if it's not, we can say visited.add next color. All right, and the set, we're gonna do the initial. Can do this, and then we say visited.add 0 and the first color. All right, and we're gonna add this, and then temp.append next color, right? And then we are going to say steps start with 0, right? And then every time we get a node out, that will be the first time we hit the node. That will be the first time we hit the node. Then we just say res. Holy moly, we want to find the shortest path. Right? The shortest path. The first time we hit it. Right? Then we just say if res node, right, is smaller than 0, then res node shall equal to steps. Do we go steps or steps plus 1? I think steps is good. All right. Yeah. We can handle 0 as well. Because the first will be 0 coming in, 0. And no 0 is smaller than 0, so we put steps 0 to it. And then we get the next color, then blah, blah, blah. Then we're done with this. Temp will equal to Q. No, Q will equal to temp. And steps plus equal 1. And that's it. We just keep going. And then we're going to call BFS on the first color is 0. Then we're going to call BFS, the first color is going to be 1. Then we will return the rest. Let's give this a shot. I mean, we have 3 test cases, which is pretty nice. Oh, so we add this is 1 1, and this turn into 3. Okie dokie. And red edge, blue edge. Oh my god. Oh. What happened, man? Okay, this is not right. All right. This is not what I expected. This is not how I'd expected. Okay. Debug. So we have to start. Step 0, node and Q. So the Q is 0 in the first color, so we got a first color. And then we get, and the next color will equal to, whatever the next color is. Because previous color is 0, so the next color is going to be 1. And for next in 0, 1, and we don't have 1, right? We don't have 1. If it's smaller than 0, we should be equal to this. Else, rest node shall equal to the minimum steps, rest node, and steps. I don't think that was changed. No, this does not change, but that's a fix. Yeah, that's fine. So yeah, if the start is 0, that means the next will be 1, but we don't have anything in 1, right? So next graph 1 is this node, it will be empty, so it doesn't do. So boom, get out. So this one get out. Now we do BFS 1. Okay, we do BFS 1. So coming in first is 1. Again, this one fine. Next color is 0. Then we go to 0, right? 0, graph 0. Oh, that is not right. A. And in fact, I think I will do math.inf on this one. Then they can be unified to this, and then we can return R for R in res if R smaller than math.inf, else -1. That looks more like it. That looks more like it. Okay, let's give this a shot. Perfect. Should you consider that as an improvement? The last time we did it, July 20th, 2019, struggled tremendously for 2 hours. Finally got it, but probably a stupid idea. Let me take a look how it looks like. And the next day, right, we go to very late. I'm like, nah, I don't want to do this anymore. The next day we got probably the right idea. Let's take a look. Oh, wow. What is this? Self to test. Dict 1, dict 2, start, edges, visited, color 1, color 2, rest, step. Oh my god. I mean, it's the same idea, right? It's basically the same idea. But I don't know why it becomes so convoluted. And color 1 plus str. That's 3.5 years ago. It's a better solution. Graph. Q for BFS. Oh, you go at 2 at a time. Can do 2 at a time. Oh yeah, look at this. Ooh, if it's -1. S is node, right? Yeah, S is node. S is node. C is color. So for N in graph SC. So this will just start. Yeah, similar idea, but I like how it is this time. I like this time, right? It's clearer, right? We do BFS, and then this is the color, right? This is the color, previous color that leading to this. And then we do use this again, and we handle this. I like this one better. Yeah. BFS. They do 3. How does it only do 1 color? Oh, -1 is undefined. Then how do you do the other color? Not equal to previous color. Color 0 and 1. You store the color. You store the color while you're doing the... I see. Yeah, it's the same. Use BFS. During traversal, we have the state, right? The state of each node is the node itself and the color of the edge leading to this node. And this allows us to decide which node to add to BFS, to the queue in the next step, right? The next node, the next state, the next combination, right, of node and color must not appear before. This means we do allow repetition of node, allow revisiting, right? Allow revisiting a node that has been visited before, as long as the edge color leading to the node is different. Other than that, it's a standard BFS. I do run BFS twice, right? Because the initial node has no color edge leading to it. So from the initial node, we can go out with red or blue. Okay. O n plus e, where n is the number of nodes and e the number of edges. Okay, we have some Ghana today. We can explore a little bit. Maybe just do 2. I don't know. Depending on how you want. Difference between element sum, digital sum. Okay, that's not too hard. What's this one? 2535. 2535. What would be the best way to do this? That's a good question. I mean, I can turn into str and go one by one. I can divide by 10 and add its, maybe I'll divide it by 10. So we have element sum, ES, okay? And DS, digital sum, right? So for any nums, while n, ds plus equal to n mod time 10, and divided equal to 10. Then we'll return abs es minus ds. That shall suffice. We run these examples. Yeah, that should suffice. MN. I'll call it MN. Okay, it's actually a good question. I like it. Increment submatrices by 1. You're given a positive integer n, indicating that we initially have n by n zero-index integer matrix mat filled with zeros. You're given 2D integer array query. For each query I, row I, column I, row 1I, row 1, column 1I, row 2I, column 2I. So we have row, column, row, column, row, column. You should do the following operation. Add 1 to every element in the submatrices with the top left corner and the bottom right corner. That is, add 1 to matrix this for all this and this. Return the matrix after performing every query. I bet you can do something similar using NumPy, but I do not know which one I should use. No, we're not going to do NumPy. Oof, 10 to the 4th. What do you think? Well, what I think is we need to figure out which one gets... Holy crap. We have top left and bottom right. So when you give top left, bottom right, anything in between, right? So it's a range. And in this range, everybody will plus 1. And then you do another one, and that's another range. And everyone in that range will plus 1. Then you have overlap. Dude. You know what? Might as well do it the other way, because n is 500. That's not big, not too big. So we can go every one. So 500 times 500 times 10 to the 4th. No. Man, that doesn't seem right. That's 2,500. That's more than a million, 25 million calls. You can time out. That's not the way. Oh. How can we? What if we have, bit for all the columns. If you have bit for all the columns, so every time you update one, and because of prefix sum, right? So everybody gets updated. No, because it has to be a range. It has to be a range. Yeah, it is a range. We're saying that we add, wait, hold on. What's range sum is you put one and then you query the range. That's a range sum. This is not range sum. This is you put a value into a range. Crap. How about matrix sum? You know, matrix has prefix sum, 2D prefix sum. Would that work? What if we do 2D prefix sum? Why don't we do have first one? Then we will get, so initially is all 0, right? And then if we add this, it's 4. That'll be, this one will be 4. I don't see it. I don't see it. So we're given the first is this, right? Everything will add 1. Everything will add 1. So this can be 1. This can be, I say it's the total. How does that help? Or binary search. You sort the query. Yeah, because all I want to know, right, is given a cell, how many queries am I part of? All right. So if we go through this, 500 times 500, right? That's okay. We can do that. And then we binary search this, right? Because that's all I want to know, like who I am in between. So how do you binary search this? Like seriously, how do you binary search this? Well, we have a key, so we can do whatever we want with binary search. We can turn this into 2 queries, right? We can do 1 top left and a 1 bottom right, okay? So let's say we have 1 is top left, and they're all just x, y's, right? X, y, x, y. They point into the top left corner. So for for you to be in it, then the top left corner for your cell, it's if your cell is on the upper left to this top left corner, then it's no go, right? It's not part of it. So you have to be your I and j, right? Your j must be larger than a y, and your I must be larger than the x, right? So somewhere to the right, somewhere down, right? So this is the region. Larger is going to be this part, larger is going to be this part. So if I binary search this, so we sort based on x, okay? We sort based on x, and how about y? If we sort based on x, okay? So binary search, I know how many. I have all of those that have their x is smaller than me, okay? Yeah, for current I and j. But all of these also have y's, right? And I need to know who has their y's also smaller than me. But their y's are not sorted. No, their y's are not sorted. Are you proposing that we do even additional? We do binary search on x. We do binary search on y. So we sort on x and we sort on y for the upper left corner. Okay? And then what? And then we can get, yeah, if we do that, we'll be able to get the candidate, right? Everything that I can be part of. And then I will have that candidate go through. I can either go through the candidate or I do another 2 rounds of binary search. Me God, 4 rounds of binary search. Can we reduce it? 4 rounds of binary search. But you have to. You wanna try? I have time. Oh my God. Which one you want? I mean, for one, I want to find everything that's smaller, right? I want to find everything that's smaller. Man, that's still everything's smaller, and we have all the y's. Are you gonna sort the y, or you sort them initially? Yeah, we can sort them initially. If we sort them initially, then we got a set. Then we got another set. We got 4 sets. 4 sets. Jesus. Okay, so x must be small. So if it's the same, right? If it's the same, that shall be included. Okay, so it's a bisect right. And the other one must be larger. So if it's the same, that shall be bisect left. You know what? I still don't think that's right. I still think it's gonna time out because we're involved with, I don't know. I am not sure at all. Well, if it times out, then this times out. Okay, queries, right? We need all the x when 4. Oh my god. Upper left x. Upper left x is upper left y's. Lower right axis, lower right y's. This. Right? 4. Upper left x, upper left y, lower right x, and lower right y. Queries. Enumerate. urx dot append ulxi ulys dot append y. This is lower right x. This is lower right y, lower right y, and then sort. Okay, for I in range n, right? It's n by n. For j in range n. Okay. Now what we're gonna do is for I or binary search. Okay. So upper left x, upper left index is gonna be bisect right ulxs I key equals lambda. It'll be a tuple 0, right? Or based on 0. Okay, so binary search based on the, oh, actually no, I is x, right? So if we want to know who has, so if the, yeah, if it's the same, because bisect right, so it will be this. So we didn't know the indices, right? The indices. So it has to be urx that's smaller or equal to. So all the indices up until URL index. So we say if URL index is equal to 0, which means I is smaller than all the x's. Yeah, these are tripping me up. I's. Okay. These are tripping me up. J's. Right, it's I and J. Row and column. Maybe row and column. Nah, this is better. I, right? Then I should be bigger. So if it's equal to 0, which means none of the UL upper left I is bigger. And it is smaller. All right, so if that's the case, then we can continue, right? That can continue. Ooh. That should happen. We're doing I, right? So this should happen here. Yeah, we're doing I. This is current row. If the row is all bad, then we just continue, right? We're doing the row. We should just continue. If it's good, right? If it's good, then we shall also do, right? We shall also do lower left, lower right index equals bisect this one, bisect left, lower left, lower right i's I key equals lambda tuple 0. All right. So what this does is I want I to be smaller, right? So if it's the same, I want from this, right? If it's the same, smaller. So anything that's larger or equal to is good, which means if I is the biggest, so if L index is equal to lan LR i's, which means it's the biggest. I is the biggest. It's bigger than everybody else. In this case, continue. Otherwise, we can say candidate equal to set and set. What's the first set? For k in range UL index, because right, okay, so we have something smaller, so we can do this. Yes, if that, and we can do ULI's K1, right? The second set is going to be for that's so P and Q. P and here be Q in range. That would be LR index towards lan LRIS. This is going to be LRIS Q1. So that will be the candidate, right? And then again, if not candidate, continue. Like if like the good one for this and good one for that, they don't have overlap, continue. So that's that. Now we're coming here, that will be exactly the same. So candidate I, right? Cand I. So now we're gonna have cand J. So now it's upper left index. It's fine. That's fine. Because we already done this. And it's upper left J's with J. So upper left J. The J needs to be bigger. So it's the same, exactly the same. Then we'll continue. Right? Because it could be lower, but it's on the left. So I'm going to continue. We'll go to something bigger. And this is going to be J and J. We say if this is equal to J's, we continue. So candidate J shall equal to J's P1 for range 0 to this, or J's Q J. If not candidate J, continue. If it is candidate J, right, then we can say candidate equals candidate I and candidate J. If len. Then we can just do it. We can say queries. Well, I never really create result equals 0 times n for this range n. Then we can just say res ij equal to len candidates. How many times we've been doing this? Which I can just do this. If it's 0, that's perfectly fine. And then we'll return the rest at the end. All right. I'm not sure. There's a lot of overhead every time binary search. And we have this set thing. Yeah, I'm not confident with this one. Let's first get this right. Okay, we get it correct, and then we worry about the performance later. It's correct here, but with a large query, I really have no clue. I'll give it a shot. Judging. I think the set operation just takes too long. Maybe I shouldn't do the set operation too early. Like this set operation. I think it should wait. Jesus. I think I should wait. What if I wait? We will try this one first, because we know these are the most the heaviest thing, right? I don't really think it's gonna be making a difference, but we can try. And binary search will be fast, so we can do this. Blah blah blah. Oh, in this case, hold on, I do have to make changes. So let's call it UL index I. Okay. This LR index I. Okay. Then we'll do this one here. That will be J. This will be J. This will be J. Index J. Candidate J will be J. That one will be J. Okay. So we not sure. We'll try this. Man, this doesn't seem to be the right way to go. Man, doesn't work. Gotta be a smarter way. Come on, think smarter. Think smarter. if we consider each row, kind of just turn it into a 1D problem. Right, we have all the upper left corner. So if we pull all the upper left corner, we find all of them has upper left corner with row number 0. Okay, so we have row number 0, and then we know where it ends by looking at that. So we have a range. Then we have another range. Then we have another range. We have all the ranges, right? Now we have all the ranges. Now, and these ranges might overlap, right? So we can sort them, right? So we have range. This basically turned into a 1D problem. We have a range. We have another range just for a single row. We have a range, and we have a range, right? If we sort these range by their starting point, and then what? And then when they overlap, how do you know they overlap? Well, if it goes from this, I just need to know how many are in this, right? So we gotta go da da, and then we hit someone, another thing starts. Then we double it. Ah, this is very familiar. And then when this one, and then we just pop it out. This is very familiar. I know how to solve this. I know how to solve this. This is just a timetable. It's a timetable overlap, right? Wait, how do we solve timetable overlap? It's a set. Timetable overlap. Oh my god, I've done this many times. We sort the set. Beginning and end. Beginning and end. So beginning, we push it in. Okay. And another beginning, we push it in. And then we hit an end, we pop it out. So from left to right, we will go from the first beginning we hit, right? And then we're gonna put that as 1. And the next one, and then next one, and we keep going, and I just 1, 1, 1, 1, 1, and we hit another one, we add to it, and it'll be 2, 2, 2, 2, 2. We hit an end, we pop that, will be 1, 1, 1, 1, 1. So in that case, that will be okay. Let's try one more time. If this doesn't work, then nah. So we need to sort everything based on I. Okay. And then for each row, right? No, for each row that's included. For each row. Oh. Hold on. We need to produce these ranges. Okay? We need to produce these ranges. So I can produce, given the first one, I can produce all the ranges, and I can put all these ranges into the rows. Wait, hold on. We need this one. I need. All right, we need to put we create another one, which has the rows are a list of ranges. Okay, so we can do a helper. All right, a matrix is going to equal to this for this in range n. Okay, and then for for ij, ij, p, and q in queries. Okay, so ij, p, q, right? So what we need to create is I all the way to p, every single one. We need to create the range. So we're gonna say for k in range. So I, j, right? So for k in range, I to p plus 1, right? Mat k dot append j to q. Right? J to q. Because it's from j to q. And then we can actually make it better. It should be a tuple of tuple, because I need to know j as the start. Because when I query them, when I go through them, I'll break it open and sort. Yes, yes. In fact, this we're gonna append j0, right? And mat k dot append p1. j0 is the start. No, q is the end, right? So we have the start, we have the end. Then we're gonna sort all of them, right? I'm gonna sort all of them. It doesn't really matter. So for every row, we add its range. This is j and q. So now that we're done with k, we go for the next row, next row, next row, next row. So that's the preparation. Okay, that is the preparation. And now the prep is done. Now we're gonna just go it one by one for each row, right? Then we just say for row in matrix, row.sort, okay? And then we're gonna call, what we call that? Num of overlap, right? Overlaps is gonna get set. Then we're gonna say for row I numerate mat. Right, and then we say for j in range n. Okay. Then we say we have the row. We need to go through row. So initial is all 0, right? So we hit the row. And then we hit the next one. How do we fill it? We can't go with this j. We have to go with a row. Because it's sorted, right? It's sorted. So we're going to say for the first one, if it's 0, we're going to add, and then that will be 1. And then go to the next one, then we're going to add again, that will be 2. And the next one, minus. Yeah, we're gonna remove it. Then that shall still be 2 when we hit the end, right? When we hit the end, then we remove it. Okay. Maybe the end we need to do +1. Every time we hit it, we fill the previous. Every time we hit the change, we hit the previous. When we remove, we hit the previous. And then we remove, and when we add, we don't hit the previous. It's only when we remove we hit the previous. Okay, so what we're saying is for index, right? For index status in row, if status is equal to 0, that's add. So overlaps.append.add index. And you say when we do this, we don't do anything. When we remove, else, this is when we remove. Now when we remove, we need to add it first and then go to the previous. So we need a previous as well, okay? So we need a pre-index. We're gonna start with 0. And then when that happened, from index to the previous index, we need to fill the same value. So we need to do another for k in range from pre-index all the way to current index. We say res I k. Actually, I can use j. I don't think I use j here, so I can use j. So res ij shall equal to len overlaps. So we fill all of them. Oh no, we still, oh shoot. We add and we add and we keep adding, then we never, I hated it. Okay, so whenever we add, we have to respond as well. Jesus. Okay, so when we add, we have to respond. We add this, right? We add this, then we need to do all the previous before we add, right? Before we add. When we add it, we need to do this before we add. They will become len. So because I'm adding at this position, right? In index. I'm adding at index. Therefore, all the previous need to add whatever the overlap is, which means it doesn't even include me, right? So the previous index to the current index, I am going to add 1. So this is previous to the previous. They're going to be the previous overlap, and I'm going to add the current one, and the pre-index is going to be the current index, right? And then the next time, if it's still an add, okay, then what we're gonna do is from the previous index to not include the current one, they're gonna equal to this, right? The overlap, which will be 1. And then overlap will be adding the index, which is the current one, and this one will move to the current one. And next one, if it's this, right, we're gonna remove. So we need to go from previous index to the current index, okay? To the current index, they need to be equal to this. And then overlaps, I'll remove index, okay? We're gonna remove this index. Remove what index? No, you don't remove the index. You need to remove the, Jesus. Oh my God. That is not right. Label. We need the label here. Yeah, we do need a label. We need to enumerate this. They belong to the same label. So we need to do the label. And then this is gonna be label. And the add label. Okay, and this dot remove label and pre-index equal to index. Actually, pre-index does not equal to index because I already added. So the pre-index shall equal to index plus 1, right? Because I remove this, I add all this, and then go to the next one is add. So that's that. And then I hope this works. Then we return this. Wishful thinking. Let's see if it works. Dude, it does work for this one. Holy crap. Alright, if it works for that. Oh, Lord, it does work. Oh, no way, it's still too slow. Holy guacamole. Ooh. I thought. Lordy, blessed me. Ay. So this one will pass 8. This one passed 19. All right, we got stuck on the second one. Hey, 3 seconds. Okay, so we need to do, I do believe this is the way to go. Okay. And the only thing is this, right? This is taking too long. I mean, We'll think about it. Yeah, this is taking too long. This is fine. Okay, this is fine. It's just, I believe this is fine. Actually, we can, if we don't run this, we'll just try to see how fast it's running. Oh no, this is gonna be returned wrong, so yeah, it's not gonna give me a good result. But it's fast, right? It was fast. So this is fine. The thing is not fine. I mean, even with the sort, I think it's fine. All right, the sort is fine. It's just this part. Yeah, it's this part. I mean, for one, we don't have to fill the one that's already 0, right? That's for sure. If I can just put down like signposts and then we run it again. Signposts. But isn't that be the same? We go through this one by one, right? We go through this, this. And then even if we put signpost, we still have to run the whole thing again. But it's not inside. This is saying for index, for every single thing, you have to go do this. For this, you have to do this. For this, you have to do this. But it's the same runtime. It is the same runtime. What do you not like, man? What do you not like? Avoiding all the zeros. I think that's the only thing I can think about. Okay, status 0, and then we say if okay, so every time we remove, we still have to do this. So yeah, let's see, would it be any better? Actually, this is not right. Here, no. Wait, hold on. Jesus. Would it be faster? Not necessarily. No, it's the same time. I don't think it's gonna pass. I will do it tomorrow.